Okay, now we begin to approach the fact that the electric field is conservative, and this is kind of a neat little set of relationships that should bring your multivariable calculus into some kind of focus. Okay, so we have a charge Q at the origin. Okay, and this is actually a three-dimensional system, so we can draw another axis, a z-axis, or whatever, x, y, z. So we have charge Q at the origin. We have the point x, y, z here. We want to find the electric field at x, y, z. Now, hopefully you've already thought that through. How do we find the electric field at x, y, z? Well, let's assume a charge little q at x, y, z and figure the force at this point. And then to find the field, we're going to divide the force by that charge and get the field at this point. Now, we could just skip to an equation for the field, but let's stay close to Coulomb's law. Okay, the force is K times big Q little q over r squared times the r vector divided by r. There's our Coulomb's law. And what's the r vector? Well, the r vector from the origin out to the point x, y, z is xi plus yj plus ck. So that when we do this calculation, well, here's our r vector. There it is. We have the magnitude r, square here and another r here as part of our unit vector, and we then end up with r raised to the third power. Now, r is the square root of the magnitude, well, square root of x squared plus y squared plus z squared. So the third power of that is x squared plus y squared plus z squared raised to the 3/2. So right there is our force. Our electric field is just that divided by q, so all we have to do is remove the q here. And we have then this expression. I'm not going to read it to you. It's just like this expression except q is removed. There's our electric field. Now, the actual question as stated didn't ask you to do this. I'm going to modify the question to where it does. So now what? Well, now I ask you to find, and what I actually asked you on the document that you had for class was to find the potential at this position. What's the electrostatic potential at this position? Turns out that's a lot easier to write down. Potential is just negative K times big Q over R. And what's negative times, well, what's R? R is just the magnitude of this R vector, and the magnitude is the square root of x squared plus y squared plus z squared. That is, R is the distance between the point and the charge. And the distance is by the Pythagorean theorem, or by whatever reasoning you want to use, but it comes down to the Pythagorean theorem, is just square root of x squared plus y squared plus z squared. So that the change in the potential energy being the work done by the field, well, not being, change in potential energy is equal and opposite to the work done by the field. But let's come back to the expression we had here and do what we need to do. Okay, so the gradient, well, the next question is find the gradient of the potential function. Well, the gradient of the potential function is the gradient of this v of x, y, z. So this or this is the potential function, v of x, y, z. Okay, v of x, y, z is this. The gradient is a straightforward calculation, not even really difficult here. Remember, the gradient is partial with respect to xi, partial with respect to yj, plus partial with respect to zk, applied to whatever your function is. Now, you should do that. Now, I pointed out in class, how do you get the partial with respect to x? You use the chain rule. The x derivative of what's inside the square root is 2x. The derivative of a reciprocal square root is 1/2 times the reciprocal 3/2 power of. Now, you write that out, reason that out, make sure you really lock that in and understand that. It's a very important example. and something you should have done, I would think, or almost certainly did, fairly extensively in your multivariable calculus course. The 1/2 that we get as a result of taking a derivative of a reciprocal square root, and the 2 that we get as a result of the chain rule, the derivative of x squared being 2x, is going to give us, well, the 2 and the 1/2 give us just a 1, and that's going to give us just xi, because we're doing partial derivative with respect to x times I. We get xi over the x squared plus y squared plus z squared to the 3/2. And when we do the derivative with respect to y, we're going to get a derivative of y squared. We're going to get a y over this expression to the 3/2. And same when we do z. So we're going to end up with the zk over this. Okay? Now, and actually I'm pointing up here. I should be pointing down here. Of course, the expression's the same here as it is here. The only difference being the absence of the little q out here, and that's not relevant to what I just said. So anyhow, it's going to turn out, and you should again, in detail, understand how the gradient of this potential function does give you this expression, which is the electric field. Okay? Well, what does that mean? Again, quoting your multivariable calculus, if a field is a gradient of a potential function, then the field is conservative. Okay? Well, this field is a gradient of this function, making this a potential function for the field. Your field is conservative, and from now the fact that the field is conservative, we can conclude that the change in potential energy as we move from one point of the field to another is equal and opposite to the work done by the field. And that brings us right into the work-energy theorem. And the work-energy theorem says, of course, that the work done by the non-conservative force is a change in kinetic energy plus a change in potential energy. And changes in potential energy due to this field go right into this equation, okay? Right into our whole understanding of work and energy.